and we'll try to tell you something about the background that lies behind optimality theory. I'll mention a little bit about it, but that will be the focus of this talk. So, cognitive science was born in the 1950s to resolve the question, you might say, can machines think? And this morning, Stu Shiba reminded us that Alan Turing said this was a question too meaningless to deserve attention, but the entire field basically has been giving it its attention. More precisely, the question that we worked on is what kind of machine is cognition? Turing's work on formalizing the notion of machine is really what makes cognitive science possible. It's allowed the field to go beyond the science of behaviorism, which psychology has become over the previous decades. It's allowed us to look inside the black box of cognition. Ironically, the Turing test is a pinnacle of behaviorism. It focuses entirely on behavior and not at all on internal processes for its assessment of intelligence. Nonetheless, the work of Turing is extremely foundational for all the work in this field. The central problem of cognitive science is what kind of computation is cognition, given what we've learned about the computation in the mind and the computation in the brain. Now, the 800-pound gorilla in the cognitive science room that's ignored by nearly everyone is that what we've learned on these two things are apparently extremely inconsistent. Today's slant on addressing that dilemma will be, how does the theory of cognitive computation connect to other theories of computation, Turing's notion of computation in particular? This is a rather new perspective for me. I'm not a computation theorist, but I hope that by casting it in this way, some of the issues that we've been concerned with will make contact with those that the members of this conference have been concerned with. Okay, so Turing's notion of computation is modeled explicitly on the calculation of human computers. He says the behavior of the computer at any moment is determined by the symbols which he is observing in his state of mind at that moment. This leads to a formalization of the notion of effective procedure, as we all know. But from a cognitive science perspective, what this is about is what I call the conscious rule interpreter. And this is something that we're all very familiar with. It's used, for example, in beginning learners of a second language who, when formulating a sentence of French, have to consciously try to remember that the adjective must agree in gender with the noun. And that stands in stark contrast with the intuitive processor, which is used by native language speakers who form adjective noun agreement entirely automatically, entirely unconsciously. Intuitive processing is at work in lower cognition for basic perception and low-level action, but we're interested in its role in higher cognition, such as language. And what I want to show is that a different notion of computation arises when you model it on intuitive processing in higher cognition, as opposed to conscious rule interpretation, the way Turing's notion developed. So ultimately, the question today is what class of function is computable by the human intuitive processor in higher domains of cognition. Now, what we'll see in a moment is that higher cognition deals in entities which are symbolic in some sense. It turns out that that question is really intimately connected to the dimension of what is the class of neural computable functions. So the topic today actually is the class of neurally computable symbolic functions. And I just want to make 3 points today, although they're rather packed points. So they will always appear here in the synopsis part of this screen. So the first is that neurally computable symbolic functions, which I've defined, characterize intuitive processes in higher cognition. There are two approaches to the theory of neural computable symbolic functions that I will try to give you a flavor for. The first one is a kind of recursive function theoretic approach using recursive equations to define functions. The second one is more of a language theoretic approach that uses constraint grammars to define languages, and optimality theory, which I mentioned, is part of that. So with respect to the first of those approaches, I'd like to talk about how nearly computable symbolic functions can be defined symbolically via recursive equations. That is to say, these are functions that are computed with neural computation, but compute symbolic functions, which themselves can be defined by recursive equations and give you some elementary results on computability in that framework. Then I want to talk about nearly computable formal languages. These are languages that provide, it turns out, a powerful tool for the science of human language, and to show that they can be defined symbolically, again, even though they're computed neurally, they can be defined symbolically by optimization in a constrained grammar. So the talk today is just merely unpacking those three claims. So, the first one, nearly computable symbolic functions characterize intuitive processes in higher cognition. Okay, first, what does it mean to say that functions characterize cognition? Well, the idea here, essential to cognitive science, is that cognition is viewed as a system of mental representations, data structures, of different information types, carrying different kinds of information, which are related in the mind by functions. For example, in lower cognition, the surface depth attributed in the representation of the image in front of me is a function of the optical disparity I have in the image, the shading and the lighting, and many other factors as well. These are all kinds of mental representations that serve as inputs to that function, the output of which is an encoding of the depth of the surfaces in the visual field. In the higher cognitive area that we're interested in, the output of the function might be some representation of a meaning, which is a function of a representation of an expression, something like a parse tree, a representation of the current discourse context, and so on. And of course, recursively, that parse tree, that expression, is itself a function of, say, a sequence of words which has been heard. Okay, so cognitive science is all about characterizing functions in this sense. Now, I want to focus on higher cognition, by which I mean domains like language, problem solving, chess, scene analysis, at the upper end of vision, motor planning at the upper end of action, and not areas like low-level signal processing in sensory or motor cognition. By intuitive processes, I mean, as I mentioned before, rapid, automatic, unconscious internal processes that are not deliberative. Okay, so, sorry. Sorry about that. What I mean by symbolic is that the representations involved are discrete, combinatorial, and conceptually meaningful. So, for example, here is a kind of symbolic representation of the structure of an English sentence, which is built up out of conceptually meaningful items such as words. Okay. So, as this illustrates, we can go very far with binary trees, and I'm going to assume, without losing generality, that all the symbolic structures that we deal with today are binary trees. Okay, my displays are sometimes accused of being overly packed with information, and that puts a burden on your perceptual system, which I hope will help you with, but what it produces is the load on your memory system, and for people like me, that's a big thing. So I'm hoping that if you are able to keep track of where we are through the albeit complex displays, it'll help you get a better feel for the argument we're trying to develop. And the way the screen is being utilized here is in 4 quadrants. The main points are always down there. Spelling them out is the role of the upper right quadrant. Comments and technicalities, which will only be of interest to some people, will typically find themselves up in the upper left. And I try to give examples whenever I can in the lower left. So hopefully you'll be able to go the sensory overload here. Okay, so to get back to the line, discrete, combinatorial, conceptually meaningful are what we mean by symbolic, and we're specifically concerned with binary trees, for which there are primitive functions for constructing and extracting elements named here. What I mean by symbolic functions, then, quite simply, are functions that take inputs and give outputs that are binary trees over some alphabet, what we call A, of meaningful atomic symbols. Now, what do we mean by neurally computable? Well, here I mean a neurally computable function, phi, to be a function whose inputs and outputs are activation vectors in some vector space, Vs. So that means these are lists of numbers, each of which is the activation value of a neuron in a network. I'm also going to assume there's an inner product, which gives a notion of distance in this continuous representational space, so it is a Hilbert space. And the outputs are computed in one of two ways: statically, by giving an explicit function that tells us what the output is for a given input. Often these will be simple linear transformations for us, in which case the functions will be called linearly computable. Or dynamically, where we have a dynamical system defined by this differential equation, in which typically you have something like the rate of change of the activation value of an output neuron alpha is some function, sigma, of its current value and its net input, which is given here. The total input is simply the activation values of its neighbors weighted by the connection strengths on the lines from the neighbor to the unit alpha. Okay, so this is a kind of automata theoretic view of the machine that we're looking at. Now, what I meant before by the 800-pound gorilla that was ignored by nearly everyone is the fact that it's rather hard to see how something can be a nearly computable function which takes vectors to vectors while being a symbolic function that takes binary trees to binary trees. And the solution that we're going to pursue, that's been pursued in this line of work, is to focus on distinguishing two levels. A level at which we are describing symbolic trees, characteristic of the mind, and a lower level in which we're describing activation vectors, which are characteristic of the brain. So, what I mean then by a neurally computable function, symbolic function, is something which is simultaneously a neurally computable function and a symbolic one. Well, what that means is that we actually have a symbolic function f together with a neurally computable function phi, a pair, and we have an embedding which takes trees in S and embeds them as vectors in the vector space of activation patterns, such that under this embedding, phi implements f. By which I mean that if f is mapping from trees to trees, and then we embed those trees in the vector space, then phi maps from the vectors to themselves in a way such that the diagram commutes. Or somewhat more pictorially, the situation is something like this. We have an input to our neurally computable symbolic function, which can be described at one level as a tree. And it is mapped by f to another tree, the output. Meanwhile, psi embeds this tree as a vector in a vector space. So each of these dots represents the activation value of a neuron with the size representing the activation level and so on. So that activation pattern is a way of visually depicting a vector. Similarly, psi embeds the output as a vector. And it's the job of phi to map, the way that f does, to take this vector and map it to that output vector by, for example, multiplying the activation values here by a matrix of weights and sending those values to the output units. So this is a picture of a linear neural network with a weight matrix that affects the transformation phi. So that's what we mean by nearly computable symbolic function. So the question then that we're addressing is what functions f can be computed this way, and what networks phi compute those functions. So obviously the answer depends on what in the world this embedding side is. So let's talk about that next. But instead of this complex tree, let's talk about a very simple one that has only these three symbols. The way we think about this tree is as follows. The positions in the trees are labeled by bit vectors, 0 representing left and 1 right child. The tree I here, the input tree, is decomposed as a set of bindings Here's the set, each of which is a pair consisting of a symbol and a position or role to which that symbol is bound. So these three symbols are bound to these three roles. That is the set of bindings that characterizes that symbol structure. And in general, we have a situation like that. The embedding that we're going to be using, psi, relies on two subordinate embeddings. This is a one-to-one function that assigns to each symbol a pattern in one vector space, space representing these symbols. This is a one-to-one map from the set of roles, positions in trees, to a vector space. This will be an infinite dimensional vector space if we're considering unboundedly deep trees. And the way that in practice, when we use this for modeling, we proceed with these mapping psi, A, and R, is to randomly choose activation patterns, activation vectors, subject to some kind of constraints on how similar the encodings should be of different roles and different symbols, constraints that are determined by the particular domain that we're trying to model. Okay, so I'll assume technically that the image of each of these symbolic spaces is an independent set, so we can talk about dual vectors, which are in some sense inverses of the image of the vectors that embed the symbols themselves, and similarly inverses of the roles. And further, crucially, the vectors that encode the roles of all the different positions in a binary tree are themselves recursively defined using the tensor product. So the activation vector that represents the role of being the left child of some position x is recursively defined as the vector that encodes the left child role times whatever vector encodes the mother node x. So using these, we can generate unboundedly many vectors that encode all the positions in the tree. Okay. So, in fact, what we have here is an infinite dimensional space for the roles. It's a very close analog of Fock space for those of you who know about representations of many particle systems in physics, quantum physics. Okay, so we've talked about how to assign the vectors, the symbols, and the roles vectors. And here's how we combine them to take our set of bindings for our structure and produce a vector that encodes the entire structure. We simply add together the tensor product of the vector encoding a symbol with the vector encoding its role. So pictorially, that looks something like this. If we take an even simpler tree like this, we can visualize the process of constructing its tensor product embedding the vector that encodes it as follows. Starting with, say, y, what we have here is the vector of activation that is assigned to y by this map. And here we have the vector of activation that's assigned to the role of the right child, R1. And we take the tensor product, which produces this activation pattern here. The activation of any unit here is simply the numerical product of the activation of the vector in its row and column, one each from the symbol vector and the role vector. That's the outer product, tensor product, that encodes the binding of y to that position in the tree. And there's a similar story about the binding of x. The left role, we combine them simply by adding them together. We superimpose those patterns, if you like, and the net result is this structure here, which is the encoding of that tree. And this scales up to as large a tree as you like. Now, a passing comment about the choice of vectors for encoding the symbols and the roles. The embedding vector in general has multiple non-zero activation values. It truly is a pattern. And this is what's called distributed representation in neural network theory. We're assuming the general case where both symbols and roles have distributed representations, and together the tensor product of these produces distributed representations of entire structures. And this, to me, is an important part of defining neural computation. computation, the use of distributed representations. Okay, so the neurally computable functions, to summarize, are functions from vectors to vectors. The symbolic functions are functions from trees to trees. The neurally computable symbolic functions are pairs of such functions related appropriately. So that's what you should carry forward to the rest of the talk. That was the bottom line of the first part. The first point here. Neurally computable functions, symbolic functions. Okay, so I'd like to now move on to the second point, which is where computability makes its appearance. I'll talk about a set of classes of functions that are neurally computable, in fact, linearly neurally computable. But I have to be honest in saying that the results are really quite elementary. They're not going to be fascinating results. So I'm going to try to give you a little bit of a feel for the methods behind them, what it's like to do neural computation of symbolic functions using vector or Hilbert space as your computational medium, but in a different way than it's done in quantum computing. Okay, so the first of the classes of linear neurally computable symbolic functions is the set B, a base of in-place symbol mappings. One of these functions maps every atomic symbol to some other symbol, or to nothing, without changing its position in the tree. So it might convert all occurrences of the symbol A to B. And in that case, it is linearly neurally computable via a weight matrix that has this form here. This is a sum of tensor products of two kinds of operators. The second one applies to the roles, and the first to the symbols. In this kind of mapping, the roles are not changed, only the symbols. And so we just have an identity map or an identity matrix in the part of the overall mapping that affects roles. And what we have here is more perspicuously written like this for our example. And it's kind of a product of the dual of A with B, which has the property that when it multiplies any symbol, it produces B as its output. If that symbol is A, it produces 0 if its output is anything else. So if we utilize this weight matrix in a linear neural network, of the sort we saw in the picture before, then we will realize the function that changes all occurrences of A's to B everywhere in the tree. As stated there. So if we look at the vector and pattern of activation associated with this tree in our vector space, multiplied by that matrix, send it through those weights, then the output is in fact exactly the pattern of activity associated with this tree, in which A's are replaced with B's. Okay, so moving on to something a little bit more interesting, we have the class of functions which are the closure under composition of the tree manipulated primitives and this base of symbol mappings. So this is a class that includes our smaller class B. It's closed in the sense that if we take a function in B, H, and another function in C, we compose H with F, then what we get is still in C. And the third property defining this class is if we have two functions in it, F and F prime, then the functions that arise from composing the basic extraction functions and the construction function themselves are also in C. So we look at the closure under composition of these basic primitive operations on trees. Here's an example of a function of that sort, and we'll take a look at it in more depth in a second. Now, the building block for the whole construction really is that there are weight matrices that neurally realize all of the primitive operations. There's one for the operation of extracting the left child of the tree. Its form is this. It's an identity matrix over the entire role space times what I'll call the kernel matrix, which is a small matrix that performs the right operation near the root of the tree. What this tensor product of the identity does is ensure that we get the same operation everywhere throughout the tree. It just copies this transformation throughout the vector space, essentially. And it's appropriate because this is a function that operates the same way at all tree depths. The second part here, the kernel, is simply this combination of an identity matrix on the symbol space, because extracting the left tree doesn't change any symbols. So this is the identity operation on the symbol part of the tensor product. This, on the other hand, is something like the inverse of the role, assigning the role of left child. And that's exactly what we want. The inverse of assigning the role 0 vector. The role 0 is to extract what is in role 0. So we take a simple operation that unbinds this, multiply it by this, and we get something which will move everything up as appropriately to take the left child of the input tree and produce it as the output. And similarly, there are such functions for, well, obviously for EX1, the right child, but also for the cons operation. There are two of them, though. It works like this. The vector that is the representation of the cons of two trees U and V, that is to say the tree formed by taking U as a left tree, V as the right tree, putting them together to form a bigger tree. That's what cons does. The image of that, the embedded vector corresponding to that tree, is gotten from the embeddings of the individual subtrees U and V, multiplying the first one by this matrix, the second one by that one, and adding them together. So that's the way all three of these basic primitive operations get implemented in our vector space. And what we can use, because of the recursive characterization of the space, which says things like this needs to be one of our functions in C if these two are, is that we can produce the kernel matrix for this new function by simply taking the kernel matrix for the previous functions f of prime and combining them in the same sort of way with the kernel matrices for the primitive operations of cons. And from these relations, we see how to take any function in C, such as this one, and encode it in a single matrix. So this is the example we saw before. This is the single matrix that encodes this function f, that performs exactly the right transformation to effect this function here. And you can see, of course, this is just systematically related to the definition in terms of its symbolic primitives. But it's a single matrix, it's not a sequence of operations. Okay, so what does this function do? Well, this function takes a sentence like, few leaders are admired by George Bush, maps it into an expression like, admire George Bush, few leaders. So what this function does is take, in fact, any tree of this form and map it into this tree to construct something like a logical form meaning for a sentence which has the form of an English passive. The point of this simply being that this class of functions actually contains many functions that are interesting for cognitive science. There are many interesting functions, of course, that are not in C. A very simple example is the function that reverses recursively everywhere the left and the right child. It's defined, of course, by this recursion relation here. It doesn't do anything to an atom, but to something which is not atomic. It takes the right subtree, reverses everything in it, and then makes that the left subtree in the output. So if we want to try to realize a function defined in this way, which is not a member of C, we can't just combine the primitive operations. The situation is this. We actually can realize this function. We have a function which is, again, the tensor product of the identity matrix on the symbols, because the reverse operation does not change any of the symbols. It just changes their positions. And so this is the matrix that does all the work of changing the positions. And if we plug this into the matrix version of those equations, what we see is that this expression turns into this equation. So to realize the reverse, what we need is a matrix P that solves this recursive equation. What we have in this equation at the beginning is a simple little bit which operates on the part of the vector space that deals with atoms. So this is the encoding of the base case here, and this encodes the recursive relation. So what we see is that recursive equations for functions now become recursive equations for matrices. And we can solve them in this way. What we have here is a sum of powers of a kernel matrix. What this does is it generalizes recursive application throughout the entire tree, all depths, whereas this kernel operation here just does the right thing on depth 1. So it extracts the right subtree and then sticks it in as the left subtree of a new tree. So this does the right thing for trees of depth 1. This generalizes it to all depths. Okay, so let's do it. All right, this is a segue to the next class, and the last one that I have anything to say about, a set of something like primitive recursive functions. The function class P defined to include all of these functions in C, and closed under recursions of this sort here. If G and H are already in this class, then so must be F, where F is defined by that recursion. So this is a set of functions that's linearly, neurally computable. But I think what I should do for the sake of time is to just show you that the situation we saw for reverse more or less plays out in a more general context to a similar kind of conclusion. We can come back if anyone is interested. Okay, so to conclude then, neurally computable symbolic functions can be defined symbolically by our recursive equations. They're still neurally computable. We know exactly what kind of matrix will compute them. And very, very simple neural network, or even simpler. It's all about taking those recursive equations for functions, interpreting them as recursive equations for matrices, and solving them. And so now we can move on to the third and last claim here, which is the most complicated one, involves the most internal structure, so it's going to take up quite a while to unpack this one. It says that neurally computable formal languages, which provide a powerful tool for the science of human language, can be defined symbolically via optimization and a constraint network. So we're going to take this bit by bit and build it up. First, what's the relation between being neurally computable and optimization? Because this is the key new ingredient that comes when we shift from talking about a kind of recursive function theoretic view to a formal language view. It's optimization. So the unpacking of this is happening up here. So the very first part of it is that neural networks can maximize a measure of well-formedness of the neural state. So an activation pattern in a network has a certain well-formedness that I call harmony. And networks can construct activation patterns that maximize harmony. This was a set of results developed in the early 80s by a number of people. So a little bit more precisely, there's a class of networks, we'll see a little bit what defines it as we unpack, a class of networks which maximize harmony, defined as here. This is the expression defining harmony in an interesting class of networks. Sigma is our monotonically increasing activation function of the neurons, by which I mean that the equilibrium activation of the alpha neuron, A alpha, when it's receiving net input from its neighbors, which was the weighted sum of the activations of the neighbors, is sigma applied to I, that iota. So if it's getting net input of this quantity, then sigma says its activation, its equilibrium value should be up here somewhere. more input, the higher the equilibrium value, but if sigma is chosen to look like that, it saturates at a maximum and minimum activation value. That's a typical kind of situation, not universal. We can get a feeling, I'm going to do this very quickly, a feeling for why this function gets maximized as activation spreads around in the network where units are responding to their input defined in this way. So, in the case which is relevant here, symmetric networks, where the weight from unit alpha to unit gamma is the same as that from neuron gamma to neuron alpha. If we take the time derivative of this to see how it's changing in time, we get an expression that looks like this. It's a sum over all the neurons of two factors. This is the rate of change of A. This is the crucial factor here. Now, this will be greater than 0 when all the terms in it are greater than or equal to 0. So harmony will be increasing in time in all networks for which the blue and the yellow factors have the same sign, both positive or both negative. So that's the condition. And what it amounts to is a simple requirement that the activation should increase whenever it is less than the equilibrium value. And it should decrease whenever it's greater than the equilibrium value. So a neural network whose neurons have a response to their input that satisfies this very simple obvious requirement and has symmetric connections, will have an activation, a harmony function which increases its value in time, which becomes maximal as computation proceeds. So, the conclusion there was that there's a class of networks, we were looking at deterministic networks just now, which have the property that this well-formulous measure of the state steadily increases, which means that it converges to some local maximum in harmony. It climbs up to a peak in the harmony landscape. We can do better if we look at stochastic networks. They can find the global maximum on a landscape of harmony. They can find the very best, not just the locally best activation pattern. Here's an example of a kind of stochastic differential equation that defines networks of this sort. The equilibrium distribution is an exponential of the harmony. That is to say, the probability that the network that is undergoing this stochastic spreading activation process, the probability at equilibrium of any given state is exponential in its harmony. The highest harmony states have a much higher probability than lower harmony states. This denominator t here is the computational temperature that determines the variance of the distribution. And this is reduced as computation proceeds, but with the consequence that the probability of being in any state A goes to 0, except for those activation vectors that have the highest value of harmony. So this achieves a global harmony maximization by stochastic activation spreading. To make this a little bit more concrete, in simulation, what we do to update the state from one moment to a delta t moment later, we change the state in the direction of the harmony gradient, going up harmony hill, as we would if it were not a stochastic network. But then we add a random quantity, normally distributed with a variance proportional to the current temperature. So the update is given here. And that means that in this network, we're on average going uphill, but there's some noise in this random process which allows us to get off of the sides of mountains which are not the highest and end up at the peaks of the highest mountains with probability 1. So this is what I'll call the optimization dynamics, d-opt, that we want in a network which is going to be responsible for generating symbol structures that constitute a language, this optimization dynamics. Now, in order to get to the language, we need to go now from just talking about activation patterns to talking about the symbol structures that are encoded or embedded in those activation patterns. So the next claim is that the neural, so this is about the relation between languages and symbolically characterizing them using optimization and grammar. So to do this, we look at how the harmony of an activation pattern is related to the structure that that pattern realizes. So if the activation pattern in the network we're interested in is the tensor product embedding of some symbol structure as some tree, that is to say, if it is the sum of activation patterns for all of the constituents within that tree, if it has that form, then the kind of bilinear form of the harmony function we saw previously leads to the conclusion that to calculate the harmony of this activation pattern, we only need to look at the symbolic constituents. We don't actually need to look at all the numbers that are the activation values of the patterns that encode those symbolic constituents. We can just look at the tree and determine its harmony. So the harmony of the tree now is just defined to be equal to the harmony of the activation pattern in the network that is the embedding of the tree. And it turns out that this can be written as the sum of terms, each of which is a harmony associated with having in the same tree two types of constituents, dx and dy, summed over many different kinds of pairs. So, for example, we might have one term in this sum, which is a negative term, which is defined to be a negative value whenever b of x is the subject of a sentence, marked plural, and dy is the verb in the same clause, marked singular. So what we have here is a constraint that assigns a negative penalty to sentences like this, dogs runs, and the magnitude of the penalty is the strength of the subject-verb agreement constraint in the grammar that is encoded by the harmony function in which this is one of the terms. This is the term that captures is part of the subject-verb agreement constraint, and the numerical magnitude of this penalty is the strength of that constraint in a grammar which is encoded in the harmony function. Okay, so next, what does this allow us to do with respect to defining formal languages? Well, languages can be defined now by symbolic harmony maximization. I'll talk about the case of formal languages first and then natural languages. So in the case of formal languages, what we're talking about are sets of collections of trees which can be generated by symbol rewriting rules. For example, in this context-free form, a collection of rules like this generates a set of trees. That's our formal language. We can specify that same set of trees by a harmony function in which we put constraints that look like this. Remember, a constraint assigns some sort of harmony value, positive or negative, depending on whether the grammar likes it or dislikes it. We can assign a positive harmony to a pair of constituents where one of them is the symbol A at some location X in the tree, and the other one is the symbol B at a position which is the left child of X. So whenever we have B as the left child of A, then we get a certain harmony benefit. And so the harmony function as a whole, which has a bunch of terms like this, will reward configurations, tree configurations, which are sanctioned by the grammar. And we have many other rules that end up penalizing those that are not. So the upshot is that we can construct a harmony function which corresponds at the lower level to a connectionist network, a set of weights in a neural network. We can construct a harmony function with the property that those tree structures that have maximal harmony are exactly those that the symbolic rewritable grammar declares to be well formed. Now, in addition to being able to study formal languages, we can also look at human languages in this same mode of grammatical sentences are those that have maximal harmony with respect to the appropriately defined harmony function. The way we're going to do this is as follows. Well, I should say it first. It turns out that by characterizing natural languages through harmony optimization, we get a description that's actually quite useful for linguistics. We've seen examples of the kinds of constraints that appear in these constraint grammars in actual natural language grammars. We saw the subject word number agreement constraint before. One other example from phonology is a constraint that says a syllable does not end in a consonant. This signs negative harmony whenever you have a syllable symbol dominating the consonant in the final position. And many, many other constraints of this form have been developed within linguistics. The empirical discovery that was made was that when you characterize languages this way, natural languages, typically the constraint strengths, the magnitude of those harmony penalties and awards, the constraint strengths, when you rank them, grow exponentially as you go from weaker to stronger constraints. With the consequence that this harmony function with those exponentially growing constraints actually defines a kind of lexicographic order on the trees. What I mean by that is this. If we want to know which has higher harmony, two trees, S1 and S2, if the strongest constraint in the grammar that has a reference between them prefers S1, then the harmony of S1 is greater than that of S2. Even if all the constraints weaker than C prefer S2. So the strongest constraint that has a preference is decisive about which of two trees has the highest harmony. So it is grammars of this form which constitute optimality theory grammars. In optimality theory, developed with Alan Prince, a grammar is an ordering of constraints, strongest to weakest, which induces a lexicographic order on the linguistic expressions, the trees, that are being evaluated as well from the ill-formed by the grammar. Okay. So the big win for linguistics is that when grammars are approached this way, we can often view these constraints as universal constraints that apply in all languages, which is much more difficult to do if your grammar consists of a bunch of rewrite rules instead of a bunch of constraints of this sort. The consequence of being able to assert that constraints are universal is that when a linguist is using optimality theory to characterize some aspect of natural language, like the stress systems of the world's languages, the linguist proposes a set of constraints which are hypothesized to be the universal constraints on, say, stress in natural languages. And now every possible ordering of those constraints corresponds to a different grammatical system. And in each of those orderings, a different set of trees is optimal. That is to say, a different set of trees is well formed. So the set of possible grammatical patterns across the world's languages is now subject to formal calculation. If the pattern appears as resulting from one of those orderings, it's a possible human language. If it doesn't, it's not. And so, for the first time, this offers a general formal theory of linguistic typology, which is one of the central concerns of formal grammar. Okay, to finish this, I want to go back to the question of neural computation of these languages. How we can actually design neural networks which will produce as outputs the elements of symbolically defined language, defined now in terms of some sort of harmony function. Okay. The problem that needs to be addressed is that it turns out that maximum harmony states are generally not pure symbol structures, but blends of structures, perhaps something like this. So we have a neural network with a continuous representational space. Some of the points in that space represent pure trees. Others don't, and they represent funny mixtures like this. So this is represented by some vector in our representational space. Turns out that the harmony functions that correspond to our grammars have structures like this as their highest harmony solutions. What we want is the highest harmony tree, not the highest harmony blend. It turns out that we can get that by adding to our harmony maximizing optimization dynamics, d-opt, that we talked about a long time ago, stochastic optimization dynamics. We can add to that what we call quantization dynamics. These are a set of connections in the network that create an attractor at every pure symbolic state. So this dynamics is forcing the activation pattern to be one of those special states that is the embedding of a symbolic tree. The total dynamics is gotten by simply forming a linear combination of the dynamics, stochastic dynamics, which is trying to find maximum harmony, and the quantization dynamics, which is trying to force us to a tree. The computation proceeds in such a way that this mixing parameter lambda goes to 0 as the computation proceeds. That is to say, the optimization is turned down and the quantization is turned up as computation proceeds. Quantization ultimately prevails, ensuring that we end up at one of those special activation patterns that is the embedding of an actual symbolic tree. Now, this has been applied to a number of applications in the science of human language. And so I'll tell you just a little bit about the types of applications that we have pursued here. There are simply two types. The first one is what linguists would call a competence idealization. If we give our network sufficient computational time, then it will compute the globally correct pure symbol structure. It'll produce what the grammar declares to be a correct grammatical tree. So we could say, here's a neural network that has a grammar and knows how to use it. This is something which we haven't had before. Being able to put a grammar into a neural network in this sense is new and is the consequence of trying to solve the problem that we posed at the outset of symbolic functions computed neurally. The second class of applications are to what we call performance as opposed to competence, the things kind of studied by psychologists, psycholinguists. Given insufficient time, the outputs of our network are pure symbol structures, but they are not the globally optimal ones. We've rushed it. The result are errors. But the pattern of errors that we get match the patterns that psychologists elicit in experiments with human language performance. So we can say that this is a network whose errors reflect grammatical knowledge, but also reflect partial activation of symbolic constituents that are similar to correct ones. So this is a novel integration of the linguistics characterization of structure, which is all about symbols and grammars. Integration of that with the psychological study of mental processes, which tend to be all about activation of relevant mental representations. Okay, so there we are. That's the final point. To conclude, I'll just go back to a question that we formed at the beginning, phrased at the beginning of the talk. What kind of computation is cognition? That is to say, higher cognition, intuitive processor, not the kind of conscious rule interpretation that effective procedures characterize. What kind of computation is cognition of this sort? Answer, neurally computed symbolic functions. And now we know what those are, something about the kinds of functions and languages which are neurally computable, but at the same time symbolic. And so I'd like to just simply thank my collaborators in this work, show you where to get more information, and acknowledge funders. Thank you very much for your notes.
Thank you very much for a very exciting talk. I think we've got time for some quick questions.
I think I can speak now.
Okay.
So there's a very basic and stupid question. So there's a class of computable functions. So do you mean that you mathematical defined by Turing? Do you mean that you have now a new well-defined mathematical class of neurally computable symbolic functions on trees? And if yes, can you give an example of a function in a difference, which is computable function on trees, which is not neurally computable, if this question has any sense?
I think it has complete sense. The set of neurally computable functions is parameterized to some extent by what class of neural networks you're considering. The results that I've told you about have really focused on the basic case of linear neural networks that are just implementing a linear transformation from an input vector to an output vector. And I can't actually tell you how far we can go in getting larger and larger classes of linearly computable functions. I believe we can get farther than these primitive recursive ones, but how much higher we can go, I honestly don't know, and that's exactly the research question that we face now. Is that a satisfactory non-answer?
In the synopsis, the first slide, you are using functions to characterize processes. That's somewhat dangerous because, processes have continuous inputs, continuous outputs. New inputs can depend on old outputs. Old outputs can depend on earlier inputs. So, for example, a robotic car. Okay, this car's driving is a process. Clearly it represents something that's high recognition. But this is a process where the inputs are, let's say, the images from a camera of the world. The outputs are the signals to the wheel and the brakes. But you don't have a function because there's also the internal state of a car, its current direction, velocity, other things that is playing a role in this behavior that is not part of your input and output. So where does that fall in your, do you then say that it's not a hierarchy process? Or do you acknowledge that there's processes that it is not correct to identify functions and processes?
I take the correction. I think that you're absolutely right that in the formalization I gave you, there is no recognition of the ongoing nature of the input-output relationship that is characteristic of higher cognition. I personally have found it hard enough to deal with this class of question without turning to that class of question, but I totally agree that it really is not a proper characterization of higher cognition unless that...
I didn't mean to deride the work. I just think that this conflation of the concept of process and the concept of function is a common mistake which has led to a lot of misinterpretations of things like the Turing thesis or the Turing conjecture, and we really should understand that process and functions are not the same thing. Well, this is an example here. I'm just saying that I didn't mean to say you should be looking at this bigger class, but it's just, we don't want people to think that you are actually tackling that bigger class at the moment.
Okay, so the field of cognitive modeling doesn't normally try to address questions like what functions can we compute. So I was trying to address those questions partly because this is a computability conference. But the main activity that we do in cognitive modeling is to take some cognitive task and try to model it, and many of those have property that you're describing. And so in such a case, we would not necessarily want to say, okay, here's the function, and do that. We'd rather have some information about a human information processing system that we want to model. And because these are dynamical models, there isn't any problem extending the work on what languages can be computed to say, can we model the online processing that occurs when words are coming in one at a time and you're doing sentence comprehension. So that's not necessarily the same kind of example as you had in mind, but it has this process element to it, and a tremendous amount of work is addressed to those kinds of tasks in cognitive science. And so using these kind of methods to put grammar and neural computation together, but to address the dynamic and unfolding process, is something that we're beginning to work with, but it's hard because the kind of computation that we're doing has a kind of natural clock cycle. You start with high temperature, you go down. You start with dynamic, you go down. And dealing with continually arriving inputs in a context like that is something that, frankly, we need some good ideas about.
I think I'm afraid that in the interest of time we really have to stop here. But I'd like to thank the speaker again and remind